Okay, so here's example 2 for class 21, and it's going to be a more complicated problem. The one I have in the notes, by the way, for some reason is metric, but I have this worked out as being in English units or US units. We shouldn't blame the Brits for our silly units anymore. So I'm going to stick with these here and then just reveal the answers as reveal the solutions as they come through here. So let's see. Gear C is 10 pounds and it's got a radius of gyration of 3 inches. We want to turn those into feet right away. The uniform bar AB has 6 pounds and it's 10 inches long. And gear D is stationary, so this is like a ring gear. So this is sort of like a kind of like a part of a planetary gear set. We might have a sun gear here in the middle that's driving C. That's a very common thing, and so the sun gear would be the input, and then there'd be like a shaft that's connected to A, and that would be the output of a very standard type of planetary gear setup. So that's some motivation in actually studying this scenario. And the system is released from rest, and we want to find the angular acceleration of gear C, and we want to find the acceleration of point B. So getting some parameters out of the way. So we have this 5, this is G with respect to A. I guess I've decided to call that G. That's a little weird. Yeah. Oh, okay. I see the center of gravity, right? So that's what they mean by here. That's what I mean is that this guy right here, that's what I've decided to call is G as part of this right here. So that's important to know. And then B with respect to A, that's 10 inches. Okay. And we turn that into feet. And RC is the radius, and that's 5/12. So let's get the mass of C is this many slugs, and the mass of A is this many slugs. So we're just taking care of that instead of doing it while we go along. We get it out of our way out front. And then we get the mass moment of inertia of C. And that, of course, they gave us radius of gyration, so that's just that squared times the mass of C. This is the mass moment of inertia of the disk. That we're treating gear as a disk. And then we treat the bar as a slender rod, so we have 1/12 mass times its length squared, and then we're able to get its mass moment of inertia. So a lot of times we need to do a kinematic analysis before we can proceed with the kinetic analysis. So we set up these things because we'll have a lot of unknowns, but we do want to get this out of the way. So when released, the angular velocities of gear C and B are 0. So the normal accelerations are all 0. So the only accelerations we're going to experience are in the tangential direction, and they are all of those accelerations will be aligned with the y direction. So if you take a look at rod AB, easy enough, we could get the acceleration at the center of gravity is the angular acceleration times the distance rg with respect to A, which we found up above. And then the acceleration of B is going to be that same angular acceleration, but we're going to use the rb with respect to A. For the gear C, we can establish that the acceleration at B is now, as it relates to this, going to be the radius of C, this distance right here, right in here, times its angular acceleration, alpha C, and so that's going to be what we're going to use as equation 1. And then we also note that we have that we could also have found. Let's see. Yeah. Sure. We also know that the acceleration at B from up here is going to equal this guy right here. So we set them equal to each other, and so we have a relationship between the angular accelerations. So that's going to be equation 2. So we know those setups right there. We have some additional information. Now for our kinetics, we take an FBD, an inertial diagram, and we set this up, and this is really for the general case, right? We don't do the mass moment of inertia about a fixed point, although this kind of is acting like a fixed point. Here, what I've done, so I have taken it about C, right? Is that true? No. Wait, let me double check something here. In terms of my, okay. I think I should have written this as being about the point B, right? Because we could call the center here anything we want. We could call it either B or we could call it C. I'm kind of like double dipping and calling it C sometimes and B at another. But that's what we're doing, is we're taking it about here, and we can see that the only force that's causing a moment is going to be this force right here, and as we've drawn it, it is going to be counterclockwise. So it's positive, and then the moment of inertia about the center of the thing. So we're fine. And you notice that we don't have to use this part right here because it passes through the center, right? So we don't have to do the effective thing. So that's why we're able to write the equation up above. And so we're able to solve for f dy, at least. Well, we have set up a relationship between here, and so we have a third equation. We should take stock as we go through is that we have one equation, two equations, but here we have three unknowns. We add a third equation here, but now we have four unknowns. So we proceed to take the sum of the forces in the y direction equals mass times acceleration, and so that's going to be the mass of C, right? But the acceleration at that point, and I'm using B in this case because we already have a relationship in terms of B. And so I take a look at the forces on the left-hand side in the y direction, and we have the force. We have the reaction force within the bar, or the bar on the disk. We want to remember that's the free body diagram side. In the vertical direction. We also have the force of the ring. This is the FD up in the y direction. And then we have the weight, right? So those are all the forces on the left-hand side. On the right-hand side, we have the only mass times acceleration is the mass of the C, and it's in the negative direction. It's because it's going downwards. We can predict that it will be moving downwards. No reason for it to go upwards. And so now we have a relationship, but here's two more unknowns. Here we already had as an unknown, actually we already had as an unknown up here. So now we're adding like a fourth equation, but a fifth unknown, right? And this is a trend that happens when we have multiple parts. So we can get rid of a little bit. We could substitute equation 1 right here, so that we can take equation 1 and we can substitute it in. So we can replace that AB with something in terms of alpha right here, okay? And we can also and we can substitute 3. So I say equation 1. I think we substitute equation 1 and equation 3 into here, right? And we're left with a fourth equation. And really, I can't see the bottom of that, but that should be alpha C right there. Now we go and march through the other part, right? So that was the kinetics of the gear. Now we take the kinetics of the bar and put all the forces that could possibly be on them, and some of them we suspect what direction that they're going to go. And then we take on the right hand side all the inertial forces, all right? And one is going to be the center and this is referencing the center of gravity. So we take the sum of the moments about point A, and this right here, really, this should be written out as the sum of the moments about A is equal to the sum of the moments about A effective, right? Because we want to make sure that we include in that effective a moment, right? Because this right here can be misleading. So here's an instance. I should have done a better job of searching for that. This is an instance where we want to be careful, because as I wrote this right here, this is not really true in the purest of sense, right? This is the general solution, the general method that applies. So we take a look on the left-hand side and all the things in the vertical direction. Are we missing one? I think we're missing one. What happened there? No, we're doing it about A. That's why. Okay. So we're doing it about A. So that's okay. So we'll see that because we treat counterclockwise as positive. We have this guy. He's creating a negative moment, right? And then this guy's creating a negative moment. And we're assuming this direction right here. It makes sense that we're assuming it's going to be clockwise. So it's negative. And then also this right here creates a negative effective moment, right? Because this is the effective force and there is the acceleration. And we can go ahead and substitute in that we know the acceleration at the center of gravity is that short distance times the angular acceleration right there. So we could substitute that back in, and we could also get rid of all the positives and negatives. And now I think I have yes, yeah, the weight is 6 pounds, right? Yeah. So we have all these, and now we have alpha, and so we have another equation, right? So we have a fifth equation right here, and we have a fourth equation, and then we still haven't used the. Let's see, come back up here. We still haven't used the second equation, this guy right up here. So the things we don't know alpha AB, we don't know alpha C. We don't know FBY, and we don't know alpha AB. I think I've said all those, right? No, alpha AB was alpha from previous one. So right here, 3 equations, and we have alpha AB, alpha AC. We don't need that one. We have FY. All right, so 3 equations, 3 unknowns. We can substitute them. So I actually walk through and substitute the things into it. We combine them all together, and we're able to find what the alpha C is going to be. And then with the alpha C, we're able to find the acceleration of B. Ta-da! Isn't that great? Aren't you excited by it? I know you are. We can all discard all that stuff. And so let's see how long this video is. 13 minutes long. Do I have the solution of this? Okay, so here's the solution based on the solution manual as opposed to the one that I wrote out. I don't know how many years ago I wrote it out. But this one uses metric, by the way. And I think this is the 11th edition. So they decided it was 5 kilograms, 75 millimeters, 3 kilograms, and then another 2 millimeters, 200 millimeters right there. But you can see here, they do the kinematics first, right? So just like we had previously said, kinematics. Let's see, make my comments and all as I can highlight these things as I go through. So first, our process is always kinematics first. To set up these relationships, and you see that they have established this relationship between the alphas. It was one of our goals. Then we do the kinetics, right? So the kinetics come next, and we do gear C, and we set up these forces that are taking place. You notice that they decide not to put a force here in the x direction. There would be a force there, but truth be told, there's not going to be one because it's not in motion right now. But actually, in real life, there would be a force there, but that's okay. We'll let it go. because the gears have a pressure angle, so there's always a radial and a tangential force in a gear because of the way the shape of the gear teeth. But here they go. They use the effective equation right there, which is what I should have done. Right, I should have written out the effective equation right here instead of using the other one. But the only thing when we're taking it about this point right here is going to be what they decided to call was Q, and then times this distance right here. And we might note that okay, the angular acceleration is coming along this direction right here, right? And but we're taking it about B, right? So we don't need to use nothing needs to happen with this mass times acceleration because we're taking it about B. And so we're able to get a relationship between the force and the angular acceleration c. So we have two equations, but we still have three unknowns, right? That QC, alpha c, and alpha AB. So we proceed, and now what they decided to do was to take these two parts and put them together. There's nothing wrong with that. We do have the weight of WC over here. So they now take the effective moments about point A, so they can eliminate a y right here, so we don't have to use it. And they go and they find here's all the weights that are going downwards, and then you still have this QC that's going upwards, so it's negative. Boom, 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 boom. And they're taking, I'm double checking my things. You have to be careful. Mass times acceleration of AB. I'm not digging this guy right here. I don't like him. I think they made a mistake here. I do not think that should be positive. Boy, I'm kind of regretting looking at these, looking at this now. I'm also, oh, I see what happened. Okay, see right here. They decided, tricky. They decided that clockwise was positive. That's why. Okay, so yeah, that's positive. That's positive. This is counterclockwise, so it's negative. Yeah, this is clockwise. AB, right? So this guy right here, he's clockwise. And then this guy right here, yep, he's going clockwise. But this guy's counterclockwise. Oh, look at that, tricky. I think that's why I decided in mind not to separate these two parts out. But it's interesting that you could do it this other way, right? Anyway, we plugged some numbers into there, and we're left with this equation. I don't know why they left G in there. But you can see that we have... here's some of that. It's three unknowns. We had those two equations right up above. We're able to combine them together, and then we're able to find the alpha c, right? And that's all. And then we're able to, with that alpha c, to find what the acceleration of b is going to be. So that's another method of doing this, and it is a trickier problem when you have multiple parts. So let's see, a camera. I'm going to put a little Easter eggs in here, right? Because we can, right? And I'll show like a guitar technique, an interesting guitar technique. This is my one of my favorite guitars here, the Gibson Midtown. There's Bill Murray. Here's Bill Murray. They can look like a philosopher. Let's turn this into a distortion thing. And let's turn on delay. And let's really make... Oh, I know why. I have a compressor on it. Okay. lot of delay on that right now. Well, what we could do, this is actually not really the guitar for, but so what I'm doing is I'm doing a volume swell with the volume knob right here, and I'm striking the string so it resonates, and then it works a lot better if you have the kind of volume pot that's easier to turn. And also it makes it better. It's like if it's a lot of times you'll roll it like this right here. You gotta get the timing right, and I don't have the timing down right now. Anyway, I thought that was an interesting thing. I just thought I'd put a little Easter egg in there. What the hell?